of the routers in the core of the network. And so basically we're going to be doing flat routing. We have no hierarchy. So every slot in an expensive core router here will equal a dentist office, a 7-Eleven store, or whatever. And so that's a routing architecture scaling problem that we have to address. Now we believe that's going to be around 10 million routes and growing. So that's pretty large, and today we can't really practically support 10 million routes in a fib. But after LISP, what we can do is if we separate the address between a locator and an ID, that the locators are the only things that are injected into routing, and they could follow this topology as you see it. So we think now that the core routers that are inside that red circle will only have to store state roughly equivalent to the number of boxes that are in, or the number of routes that are inside that yellow circle. And we think that's drastically a smaller number, probably 10 to the fourth or something. And when you think of it that way, you could actually implement a fib with a 65,000 element array and just do a direct access to do forwarding. You wouldn't need to do complex data structures in your hardware to do fib forwarding. So the growth in multi-homing is really where we want to focus the LISP effort, because not only do we have to fix the problem on the last slide, we also want to be able to provide features, useful features, to make it compelling to deploy the new technology. So basically you have a site, and the number of multi-home sites are growing pretty rapidly. And a multi-home site is just, typically it is 2 or more routers, 2 or 4, depending on what your redundancy level is and if you're multinational. And you have 2 routers connecting each with separate links to 2 different service providers. That's pretty much the basic definition of what a multi-home site looks like. What we want to do is we want to improve site multi-homing. Today you can control which way packets egress, because it's basically you take full routes in your site if you choose to get shortest path exits per destination. And when you just want the shortest exit, then you just inject the default route from R1, R2 in there, and then the sources that are closer to here use R2, and the sources that are closer to there use R1. So really the policy on how you egress packets is done locally, and that's quite nice. Of course, incoming, you don't have that luxury, because it's some router in the middle of provider A or provider B that's doing BGP shortest path or best path selection that's deciding which packets come in. But we want the sites to be able to control their ingress traffic too, especially if you have sites that are not necessarily providing servers but more clients, and so all the HTTP return traffic is coming down. You want to be able to use your links that you're paying for. So we want to be able to control that at the site and not have a BGP AS path or local pref or MED policy decide which way packets come in. And we want these boxes to be relatively low X. You need a PhD in BGP to get this to work today, with longest path, match lookups and running BGP and playing around with policies. It's pretty difficult right now to make that work. So our goal is to possibly not, if BGP is running there now, that you'd be able to get all the policies and do them locally without running BGP in those CPE routers. Now, if we can improve site multi-homing, if this is a service provider where it's acting as transit, we could also do the same sort of thing as well, because service providers today can't control their ingress packet flow. So everybody just says it's a wash. I'm going to send you a bunch of stuff on these links because I know you're going to send them back to me on a different set of links, so it's just going to wash out. But so what we can do is, with another level of indirection, we could actually use LISP to improve site ISP multi-homing as well. Now, if we decouple the site addressing from the provider addressing, what we can do is we can avoid renumbering. What we do is, if we have a set of addresses that are being used at the site that are not in the core routing tables and the core routers know nothing about it, you could actually allocate addresses there and never have to renumber again, because you don't have to worry about addressing the site to make the internet scale. You can make it a local decision, and it's completely decoupled. So you can allocate lots of addresses to the source. You can decide what your exit and ingress policies are, and the core routers don't have to pay for it. So it's a local tax, not a national tax. That's what's happening right now. Today, to do these sort of things, you have to inject more specific routes into the routing table. And if you inject a more specific Sprint route into the AT&T network, they have to carry it all the way through. And so that means, because you want ingress on that AT&T link, AT&T and everybody in the internet has to pay for an extra slot in the routing table for your ingress policy. So we really want to do things locally and be able to be good citizens globally. So basically we'll have two separate namespaces, as Noel Chiappa calls them. They're really address domains, where if you're just looking at IPv4 right here, there would be two different 2 to the 32 addressing domains. And the green ones, throughout this presentation, where you see green, we're talking about EID prefixes, endpoint ID prefixes. And where you see red, we're talking about locators. So the locators are the aggregatable entities that will be routed on, which the core routers will know about. And the EIDs will just be used to move packets around inside the green area and to be used for TCP connection IDs and that sort of thing. Okay. So if we can do these 4 basic multi-homing features at the same time, we reduce the size of the routing table, and this is goodness. So what do we have to do? We have to separate the IP address, or separate the semantics of the IP address, or break it apart, or add another address. There's all kinds of ways of doing this. If you have a really long address, you could really break it apart pretty easily. Today, IPv6 and IPv4 addresses mean both who you are and where you are. So if you decide to move and you want to be able to be the same who, then you have to inject where you are into where somewhere else, and you can't aggregate. But here, what you could do with an IPv6 address is you could say the lower order 8 bytes are going to be an endpoint ID, and that stays fixed, and that's how I'll define a TCP connection or a UDP socket. And that means the higher order 8 bytes can actually define where this host is currently sitting at the moment. And if this particular host moves around, it can keep 11223344, but the higher order bits change. So the higher order bits are looked as the locator, and the lower order bits are looked as the EID, or the identification. So that works pretty good with IPv6, right? There are some checksumming issues with TCP, because today TCP looks at the full 16 bytes to do a pseudo-header checksum. So there's some issues there, and people have addressed it various ways. We're going to address it a different way, where you don't have to change the host when you deploy LISP. Now, if you look at IPv4, there's not enough bits to split it up. There's really not enough bits to have enough uniqueness in IDs to support lots of connections in your host. And there's not enough bits in the locator side to be able to put enough hierarchy in the network. So what we have to do with IPv4 is we actually have to add another 32 bits somewhere. We obviously don't want to change the IPv4 packet format. That's pretty much a non-starter. But if we put another 32 bits somewhere else in the packet, maybe in a new header in front of it, that we can then have the 32-bit locator in the outer part of the header and the 32-bit EID on the inner part of the header. And I'll show you that in a second. So that's how we would split up or make a new type of address for IPv4. Now, you don't have to change that address. That 209.131.36, I don't know what that address is. I think it's Google. But that address could be the address that you currently use today for that host. You don't have to change it. So if that turns out to be a provider-independent address, you just keep using it, and you can use it as an EID now. Okay? If it's a PA address, then, and you stay connected to the provider who allocated you 209.131, then you just use that as a locator, because it can go into its aggregatable system. Okay? So why do we want to do the separation? It provides a decoupling and a level of indirection that allows you to keep one thing fixed while you change something else. Now, by keeping the EIDs fixed, it means you don't have to renumber your sites, but now you have the option to home to new providers. You can switch service providers much easily. You could actually move a little bit. And we're very careful about using LISP for fast mobility, but you could keep an EID attached to a host, and the host could move while the locator changes, depending if you're at home, you're at work, you're at Starbucks, whatever. But we're careful about that because of the mapping scaling problem, which we'll talk about in a second. So we're creating these separate namespaces that have different allocation properties. And the basic terms are, we call these IDs and locators EIDs or RLOCs. And basically the end site, these EIDs are end site addresses for hosts and routers at the site. They're the addresses that you're using today. You don't have to change them. The records, the A records that go in DNS do not have to change. Those continue to stay the way they are today. We just call those addresses, those 32-bit values, EIDs. And we hope that those addresses are never seen as a destination address inside the core. That's the goal. And we want to make these globally non-routable. So as your site converts to LISP, these addresses that you're injecting into routing now are withdrawn from routing, and then they're kept in your site. And it's your locators that are attached to your service providers which stay in routing. So day one, when you implement LISP, you get the benefit. That's our goal. We don't want 50% of the internet to convert before everybody makes benefit. You have to benefit as you go, or you will not go, right? So that's the way it has to work. Infrastructure addresses for LISP routers and ISP routers don't have to change either. Okay? All we're proposing is the sweet spot to deploy LISP is in the CPE devices at the site. And hopefully what we're trying to do is maybe this is only a software upgrade to those CPE routers. We may not even have to change hardware. And this is a fast deployment model that we could do. Hosts do not know about these locators. They're basically, I don't want to really say this, but they kind of look like a label on a packet that goes through the network. And I won't even associate it with a name of a certain technology. So basically, again, the RLOCs or the locators are in the core, and the EIDs are at the site. And now we're going to talk about specifically what LISP is. So LISP stands for Locator ID Separation Protocol. The ground rules and the fundamental goals is that we want it to be a network-based solution, which means you only have to make changes in very few devices at the sites to make this new architecture implemented. No changes to hosts whatsoever. We will not bail down from that. We have to have no changes to hosts. And we've been able to prove that so far in our pilot deployments. Dave will talk quite a bit on that. No new addressing changes to site devices. Very few configuration file changes. We found that you didn't have to change any configuration files in existing boxes, but you do have to configure LISP on the CPE routers. That's probably obvious. And it's imperative that this thing be incrementally deployable. And it must and does work for IPv6 or IPv4. So we can do all combinations of IPv4 EIDs over IPv6 locators and vice versa. Basically, the model is called a jackup model, which means you put a new IP header on the packet that comes from the host builds this packet right here, or builds these headers. And the destination and source and destination addresses here are the EIDs. So if the source address is the DHCPable address or the IF config address, the destination address is what you get from DNS. Nothing changes today. When the packet makes its way through the site to the CPE router, then the LISP router supplies or prepends a new IP header, and in the outer header are the RLOCs, or the locators. The source locator is the IP address of that router, and the destination locator is the locator that's associated with the EID that's in the header. And how you map from that to the next is we'll present to you in the next couple slides. So it's called a map and an encap because you have to map the EID into a locator and then you encapsulate it. This is how the packet format looks. This is the outer IP header right here. And as I said, the source and destination routing locators go in the source and destination fields of the IP header. This is the guy doing the encapsulation. This is the locator. This is the CP router at the destination site that's associated and supporting this destination EID. This is the inner header built by the host. And we have 8 bytes of LISP, and we'll talk about these in a minute. And then we have a UDP. Very important why we use UDP as encapsulation. Because whenever you use any tunneling technology, those poor core routers that are attached to a directly connected router with a lag, they think it's a single flow, so they polarize all the traffic on one of the members of the lag. If you use UDP and the encapsulator changes the source port number as it encapsulates differently, then the guy who's attached to the lag thinks they're different flows. So the encapsulator actually does a 5-tuple tuple on these fields, and then sets the source port uniquely for that 5-tuple hash, so the lag router knows to load split the traffic across the members of the lag. Really important. Also, we want to get through firewalls. I spent this last week trying to get my box working through a Linksys firewall, and it was really challenging. Actually, that wasn't the hardest part. But anyways, UDP goes through firewalls much easier as well. Now, you can imagine that what we just showed you was this sort of thing where we had an IPv4 header that had locators in it, the LISP, and then this is what the host did. Well, there's no reason why IPv6 could be originated by the host, and then we run it over IPv6. So this is kind of the homogeneous model. But we already see cases where, what if two sites are running IPv6 from the host all the way to the border router, and the destination also does as well? Well, you can map, there's no reason why you can't map IPv6 EIDs into IPv4 locators. So we can have two sites talk to each other with pure IPv6. They don't know anything about IPv4, but we just use the infrastructure or the substrate IPv4, the capital I internet, as we know it today, as the transport between the two. So the CP routers would just encapsulate those v6 packets in v4. That's a no-brainer. It just works. And then this is the case where it could work the other way around. Say China goes to pure IPv6, and you wanted two IPv4 islands to talk to each other, you know, that's how you would do it. So we can work any combination here because an EID is just a sequence of bits, and a locator is a sequence of bits. And the sequence of bits that you use for the locator, if it's a 4-byte value, you encapsulate with IPv4 header. If it's a 16-byte value, you encapsulate with an IPv6 header. Pretty simple. So there's no NATs that are required to be able to make this work. And arguably, if you wanted this to work, you might have to use some kind of NAT PT or that sort of thing, or do a double NAT to go from and to based on these transition points. But here you don't have to do that. It's just tunneling. So what is LISP? There's a data plane and a control plane, obviously. The data plane defines how the encapsulation works and the decapsulation works and where you can put your tunnel routers. Like I said before, we think the sweet spot is at the CP router, but there's no reason why you can't put the encapsulator maybe close to a server and a decapsulator closer to the edge. It depends if you want to take full routes, the full locator routes, you want to bring those into the site. There's all kinds of deployment ways you can do that. The data plane is also designed to give you some form of locator reachability. Those locator reachability bits you saw in the LISP header are used for that. We'll talk about that in a separate slide. And we have a data-triggered mapping service as well as a control plane mapping service. At the control plane, we have to design a scalable mapping service. We have to be able to map from EID prefixes to a set of locators. And we've actually came up with 4 proposals that are called CONS, NERD, ALT, and EMAX. And we'll talk about that in a second. The guy who does the encapsulation is the ITR. The guy who does the decapsulation is the ETR. And when we're talking about direction, and we're saying when the ITR does a mapping lookup, meaning that should tell you that the packet is coming from a source in a site, going to an ITR that has to do a lookup to encapsulate. And then when we talk about the ETR, we're implying direction that the packet is coming from the core. When we refer to a box as an XTR, we're not talking about data flow. We're just talking about that object called the list box that's providing XTR, either I or E functionality. So let's go through a unicast packet forwarding example. If you look at these two sites here, let's say that their EID prefixes are allocated from PI space. So here's 1/8, and this guy's out of 2/8. Has nothing to do with the topology that they're associated with. We have a source on the left-hand side and a destination on the right-hand side. They're both multi-home to separate providers. Now, it turns out that the address of S1 is allocated 10001. It is a PA address from the provider that it's attached to. And S2 is the same out of provider B, and it's a mirror image on the other side. Okay. Now, what happens is S1 will want to talk to d.abc.com on the right-hand side. It's going to get an A record back 2002. That's the same thing it gets back today. If you converted these two sites to LISP, it would still get that 2002 today. So what S is going to do is going to originate a packet from itself. And there's a cockroach going across my keyboard now. He must not like LISP. That's interesting. Maybe he does like LISP, yeah. Okay. There, I got him. Okay. If he would have went across the screen, then I could have seen the policy route he took, right? But anyways, so S originates a packet from 1001 to 2002, and that basically just finds its way to the edge. And the reason it does is because 2002 is not in the IGP. It's not one of the subnets in there, so it's going to find its way to the edge. Let's say the policy here in this source site is that he's S1 and S2 originating to the fault. So if S is closer to S2 and he's using a shortest exit policy, the packets are going to egress S2. Let's just say right now, for the sake of this example, that S2 does have a mapping entry for the destination. It has a mapping database that's used at forwarding time. It has a mapping database that describes an EID prefix. He doesn't have to maintain every EID at the destination. It could be the EID prefix for the entire site. So we do have aggregation of routing table entries on a per-site basis. So that EID 2/8 will map to these two locators. These two locators are the IP addresses of those CPE boxes. And it turns out that this site has decided that those are, okay, what happens is this site goes to Aaron, and Aaron gives him 2/8. And then the site goes to provider X and says, I want to connect to you, I want to buy service, give me a locator, so it allocates D1 12002. And then they also go to provider A and they get 13002. So the site basically puts this binding together and is configured in these two boxes. Okay? Since we want to be able to support 10 to the 10th mapping entries, we can't have a central database. This is just similar to DNS, right? You can't put, at one time Etsy hosts worked, at a certain point it just doesn't work. So we have to make the database distributed, okay? And only the people that need to talk to who they need to talk to get it when they need to, okay? So what happens here is the policy at the destination site, they say, I want to use both of these with the same priority, which means I want everybody to equal cost load split their traffic across these two locators. They're the same bandwidth, I pay the same amount, I want to use both of them equally, okay? And that's what the weights are. The weight is I want to do 50-50, okay? That policy now of the ingress traffic flow is done by the site and not by some core routers that are in that, you know, provider A. In today's world, provider A may decide how they get to D, and it may not be through D1, it may be through D2. What if site D wants to be able to say, I want all packets to come a certain way from provider A customers? So what happens is the packet comes to S2. S2 says, okay, I'm going to do a longest match lookup in my mapping database for 12002. I find 2002. I find this entry, and I'm going to hash, since they're equal, I'll do a hash to pick one. So for this particular EID thing, EID pair, I'm going to go ahead and use 12002. My IP address is 11001. I'm going to put that in the source. You know, so when this guy receives the packet, he does know that there's a locator associated with this /32, which is one of these locators. That's kind of interesting too. There's an ability to glean and there's an ability to spoof. So choose which one you want to do. You have to take the good with the bad. But the point here is that this guy then injects the packet to provider B. Now, what is provider B doing? He is not routing to D. He is not routing to 2002. He is routing to finding the shortest path to provider X. A packet has to get to provider X. And that's a BGP policy in how it gets to provider X. Once the packet gets to provider X based on shortest path AS or best path selection based on what provider B decides, it could decide which way it goes. But once that packet gets into provider X knows it's for my customer. It's not only for one of my customers' hosts. It's one of my customers that's on the other end of a PEC link that I have routing for. In other words, it's destined for 12002. So that packet will come over this. Over this path. There's no other way it can come anywhere else. There will be no more specific route injection where 12002 will come in through this path. We have to not do that or we don't solve the routing table problem. So what happens is the provider X PE box right here decides just to send it over the link. The D1 guy says, it's addressed to me, I just decapsulate. He decapsulates and then forwards it based on his IGP routing tables into D. And so that's basically it. It's just a tunnel between these CPE, the ITR and the ETR, and it's all done on locator addresses in here. That's the fundamental idea. Now what's new and what has to be explored, which is kind of researchy that we learn every day about, is how to scalably get this mapping database. Go ahead, Dave.
I just wanted to make a brief comment. I thought it was going to be easier. Basically, Dina said it's a tunnel, but it's not, you know, how many people configure GRE or something like that on their routers? It's kind of a pain to manage that, right? These are dynamic tunnels. There's no interface associated with the tunnel. It's an encapsulation, and in that sense it's a tunnel, but there's no state in the CPE associated with that tunnel. It's an important point because when we first started doing this, people said, oh yeah, we could just put up GRE tunnels between all these things. And then we realized, well, first off, there's all that state, but secondly, we don't even know where the other ends are. So, and we didn't want to have to do the coordination job between, you know, here's your tunnel source and destination, all that. So it's a tunnel, but it's not like a GRE tunnel where you have an interface, some kind of interface or some state in either side.
So, you know, us router vendors have built lots of technology that has done tunneling, and mostly when people think of it, it's always, we've done it with interface tunnel 0, and that static tunneling stuff was always a scalability problem. Managing lots of interfaces in these boxes are much harder than managing lots of routing table entries. So like Dave says, is these are dynamic encapsulating things. I won't even call them tunnels anymore, but what we have to manage is a new database, which is this. So, you know, there's no such thing as a free lunch. We have to add something new to get this new thing. What we're adding new is this mapping database. And we'll continue to talk about that for the rest of the presentation. But of course, since I'm a multicast guy, I can't forget multicast. No solution would be complete without multicast routing, right? Everybody's going to shake their head here, yes? So
How many people have multicast running in their networks?
Oh, so Jose cares. Oh, so I can't skip over this. It's pretty simple, though, the multicast, well, maybe that's an oxymoron. We still want to be able to keep the EID state out of the core network. And that's what we've done for unicast, so we must do it for multicast. You know, in multicast, we have these entries called S, G entries, which defines a source tree from S going to group G. So we want that, if that source state is EIDs, then we've taken this EID state out of the core for unicast, but we can't put it back in for multicast. So we have to have this consistent design goals for both of the types of forwarding paradigms. And we also don't want to do head-end replication, because as these video services come out, you're going to kill your head upstream link. So we have to actually run native multicast if you want to benefit from using replication where the divergent points happen in the network. And we want packets only to go to receiver sites. We don't want to be flooded everywhere. And again, we want to still not have changes to hosts, site routers, or core routers. And we want to use existing protocols. We still have to make this incrementally deployable. So basically, we have these two types of entries depending on where they sit. So we basically have to concatenate these trees. The trees that are built at the receiver site have to be concatenated at a tree that's running in the core that has to be concatenated with the tree that's running at the source site. Now, we believe that group addresses are pretty opaque values today. They don't define topology. They don't define identification per se for an individual host. They do identify a multi-participant sort of communication media. And so the group address is kind of an ID there, but it doesn't have to be mapped to location. So group addresses can be left alone. We don't have to deal with them for a locator ID split. However, if you build source trees from the receiver domain to the source domains, the source address has to be dealt with, because we have to know if the source address is an EID or a locator. So that's why we distinguish between the SEID and the SRLoc. And basically, the SEID is the IP address of the source host, like it would be done today when it injects multicast packets. And that state is only kept in the source site and the receiver sites. And then those get mapped to SRLoc, Gs in the core. Here's an example. Let's say in the bottom two are receiver sites, and we have two receivers down here, one here, and that's the source that we want to join. Those green dots are PIM routers, okay? So we're assuming we have native multicast running in the core and at the sites. What happens is when this receiver down here joins, and he joins SEID, G because he got it from a directory or a web page or whatever, but he's actually wanting to join the host. So that join will follow the exit path as well. And of course, what the ETR has to do now is find the locator that's associated with this SEID. And just like when it's sending a unicast packet, it has to do that, it now has to find what the RLoc is, the locator is, for sending a join. So don't forget, multicast, unicast works like this. I send you routes, you send me packets, right? In multicast, what happens is you send me routes, therefore I can send you joins, and then you return multicast packets. So it's a three-step process. So here you have to stand on your head and say the mapping entries are used for the join packets, so the multicast data packets could come in the opposite direction. So what happens is that this guy then finds out, this R11 finds out that SEID has a mapping for this site, and that there's two locators, S1 and S2, and then it decides to use S2 based on the priorities that we showed on the previous slide. There are a separate set of multicast priorities from unicast priorities, so your ingress policy could be different for multicast versus unicast. Okay? So what happens is this guy launches a PIM join throughout these boxes for S2, RLOC. Of course, these guys have routes for S2, this 11 network, because it's in the locator space. So these guys, these PIM routers only keep the locator stuff. What happens is once the packet's here, this guy knows he needs to forward data packets that he receives, but he doesn't know the EID that's associated. He has to build this part of the tree. So this guy also, over the top, has to send an SEID, G join to complete this part of the tree building. So he does that, so there could be an EID, G state in the source site. Then then I'm saying down here, this guy does the same thing. And then what happens is we find right here is the fork point. That's where the replication will occur to send the packets to do different sites. Oops, go forward. And so the data forwarding would occur here is that the packet would travel on an EID-based tree in the source site. It then would be encapsulated with 11001 as the outer header. G would stay the same. The packet would be forwarded here. These guys would all RPF on the address that's in routing. It would come down this link, that link, and then the SEID trees here would forward internally. And that's how multicast would work. And that's showing how it would work, what the packets would look like. Questions?
That's simple, right?
Debugging is not bad. And Dave will go through all of that. It's really miraculous how we can use the existing network management tools because we made the right choice on the mapping database algorithm. And thank you for the segue to the next part.
I think there's a question.
Oh, next question? Go ahead. Can you use the microphone, please? I'm being asked.
Sorry, the question is more, maybe not technical, it's more from the political side. And what happened with the privacy? So if you have divided the information into sites, who coordinates that table that said who is who? And the second question is, I'm part of the CCTLDs organization in Latin America. How does CCTLDs need to make changes in the internal process to, for example, have LISP in .pe in Peru or something like that? Thanks.
Okay, let me answer the first part. So the privacy of information is just as private as the routing information today. This is routing information. Yes, anybody could find out who www.abc.com is, and you can also find out if for a particular ID prefix who the locators are. So it is public from that standpoint. If you want to authenticate that the bindings are right, we have to figure out a way to authenticate the bindings to make sure that someone's not spoofing something. Yeah, go ahead.
What we're kind of hoping is that the CIDR working group in the IETF will provide us some solutions, some tools for this. We're trying not to reinvent the wheel, basically, on that. You know, I mean, if they come up with something good, you know, some certificate structure that we could use, either directly or with modification, we're going to try to do that. I mean, what's your thought on that? Does that make sense to you?
When I go through the example of LISP alt, you'll see that how we use BGP and that we could use CIDR possibly to solve that problem. Now, in terms of the processes, I'm definitely going to turn that over to Dave because that's a hard question. Allocation, I'm assuming, do their address allocation policies have to change now, and do their processes have to change?
I was a little bit confused about your question because you prefaced it with the CCTLD thing, which is sort of a DNS question, right? Okay, the DNS, as I think Dino said, the DNS really doesn't need to change at all. At all. What goes in the DNS are these EID things. And from the perspective of, I guess, LACNIC or whoever is actually allocating addresses to people and whoever's controlling the CCTLD, I don't think they'll see any operational change. as far as I understand.
Yes, but in a special case in Latin America, you have some CCTLDs that have the first block's IPs, so working at both sides. So for that way is my question.
I'm not sure I understand. What do you mean by first block?
How to say?
I'm sorry.
When in Latin America the CCTLDs started with the first block of IP numbers, so they delegate directly to the user, final users. So they have in that side a responsibility to not only with the domain names or with the DNS, they have a responsibility to, like LIRS, for example, in Mexico or Brazil, that have maybe.
Are you saying that you're doing the address allocation
yes,
as well
yes,
as the?
Yes.
Oh, okay.
They have the both functions.
Yeah. That's a really good question. We have been so the question really is. Let me see if I can summarize. Okay. I think the question is, how do EIDs get allocated? Is that right? Okay. I'll talk about that, but briefly, we don't know. But what we're hoping for, and this will become clear when Dino talks about this, is a little more when he talks about LISP alt. What we're hoping to do is build a hierarchy delegation where the RIRs are at the top. So LACNIC, we're working with Roque as a sort of proxy for LACNIC right now. We have RIPE-ARIN and APNIC. And we're trying to work with them, and we'd be glad to work with you too, to kind of get a better sense of what would work for you guys. Because I think, because Dino hasn't gotten to this yet, but because the EIDs also need to be aggregated, it makes most sense to have the RIRs at the top of the delegation hierarchy. The difference, there's a lot of differences in that from today's model, and not the least of which is the RIRs don't really have an operational role right now. And it's not only LISP that's saying RIRs need an operational role. It will be there for CIDR too. So, keep an eye on that while we're talking and let us know what you think.
So what do we do when a LISP box, an XTR, has no mapping? So we need a scalable EID to locator mapping lookup mechanism. And basically, there's only so many ways to skin a cat. We could push everything to everywhere, or we can pull it when we need it. Pushing everything everywhere has transmission costs, storage costs, lookup costs. Query and reply is more on demand. You store only what you use, but there's a lookup latency issue. Okay, so you can have packet loss characteristics. We don't think at the scale we want to build that we can make it like a BGP routing table. There's just too much stuff to put around. So we do model it off of more of a query reply DNS type model. So how does one design a mapping service? You need to map before you encap. So we needed to trade off push versus pull. So we looked at this proposal called CONS, where we did a hybrid, where we would push EID prefixes at the higher level of the hierarchy, and then we would pull by sending requests along that. After thinking about that, we said, well, we could probably push EID prefixes out of BGP and do them in highly aggregated ways because we're not dependent on the physical topology and the business relationships between interconnects, providers, so forth and so on. So we thought by running another instance of BGP on a tunnel topology, which is what alt is. Alt is a alternative LISP topology. We thought that had the most promise. So let's just look at alt and see what it is. So the mappings are still authoritative at the site. You still have this database which is completely distributed. Everybody configures their own mappings, their own EID to locator mappings, just like you would do in your own domain names for DNS. And you would advertise the EID prefixes in BGP, not the BGP you know and love, a new instance of BGP that perhaps runs in a different VRF that runs over a set of GRE tunnels. Those GRE tunnels are static, they are secure, and they are pre-configured on each end. The ITRs then get the mappings by sending routing a map request, which is a new LISP control message, over this VRF or this alternate topology. And so the map request is following a path based on the BGP EID prefix announcement. And then the map request actually makes itself to the right place, to the destination site you want to send data packets to. and then the map reply comes back from that ETR. Go ahead.
One way to put that a little bit more simply maybe, or summarize that is, so you have this other version of BGP, same thing BGP, everything the same BGP, but it's running on an alternate topology in a different verb. Okay? And the only thing the thing is used for is so that you can send map replies, and those map replies will find their way to the ETR that's authoritative for the mapping. Now, why does it find its way to the ETR that's authoritative for the mapping? Because that's the ETR that advertises the EID prefix into this alternate thing. So it works. So it's only used for that one purpose. So keep that in mind when you're listening to this.
So what Dave just said is going to be shown right here in this pictorial. We see we have these EID prefixes on the right-hand side, and we have these new boxes that you deploy on the network. They don't have to go in existing routers. They could actually go in Linux systems. They can go in low-cost routers, but we call them LISP alt routers, and those are the things that are connected together with these GRE tunnels. Okay, so the sites, the ETRs themselves, ITR in the ETRs can be connected to LISP alt directly, or you can have just a GRE tunnel into it, and so they don't have to run BGP. We're going to have these different versions of low OpEx XTRs that you want to be able to implement. And so the idea.
Just say one more thing.
Good.
Okay, so the dotted line, the low OpEx thing, all that comes down to is how many people have customers that you statically route? You have statically route, right? Well, all that is a statically routed customer. They don't run BGP. Statically routed for purposes of this alt thing.
So what happens is this alt router would say 240.210/24 is reachable over this tunnel, and therefore I'll inject it into BGP and advertise it to all my eBGP peers that are over this tunnel specifically. So what happens is these two guys here that are running BGP would advertise their prefixes into this guy, and then this guy would do an aggregation, right? If somebody somewhere else needed something out of 240.1, you could just rehome the tunnel, put a tunnel right here. It doesn't matter where they physically are. We believe, and I mentioned this on the RG list yesterday, that this will run and scale better and be more stable than the underlying BGP because the topology won't change that much. The tunnels won't flap because the underlying infrastructure is robust to keep the tunnels up. And you will always rehome to this address allocation hierarchy, not physical topology hierarchy. So we can actually get really good aggregation in the core here. That's the goal. So what happens next is that this guy wants to send a packet here to 240.1.1.1, and the ITR does not have a mapping, so he can't encapsulate right now. So what he has to do is he has to find the mapping. Of course, this guy's the guy who has to answer because he's got the database entry for this EID prefix. So what happens is he will inject one of two methods, a map request or the data itself. We have the school of thought that you can't drop that data packet. So I want to be able to deliver that data packet. So what happens is we say we have something called a data probe, where the data probe is actually sent across here, and then this guy treats it as a map request and replies back. Now the people who hear that then say, oh, data probes are going to take a longer path than the underlying. I'd rather not have that happen. So the other way you can do it is you can drop the packet and send a control packet called a map request. Well, we support either way, and we default to sending map requests. No more discussion on that because it's been driven to death for the last 18 months. So what happens is this packet, as you can see how it's addressed, is the outer header contains the EID, the same as the inner header, and that's sent on the tunnel. Now, all these routers know how to route to these addresses because it's in a different infrastructure, right? So the packets are then sent hop by hop over these tunnels, and they make their way to the ETR. The ETR says, that's for my EID. Right? And these tunnels, these BGP connections are secured with MD5 or SHA-1 or whatever you want to use. And maybe later in the future can use CIDR so we can actually authenticate these EID prefix originations. But what happens is that the ETR then will then decap the packet if it's a data probe. If it's a map request, you just send a map reply back. And that map reply goes back underneath. He knows the source, which is this box right here. So he sends it back to the source of the map request, and he uses himself as the source for the map reply. And the map reply it goes back underneath, and then the guy gets the mapping entry, and then subsequent packets get out encapsulated. That's fundamentally how you have to do it. Now, Dave will talk more about this, but if you want to find out which paths your map request is taking, you just put this box, you tell the CLI there that you want to go in a non-default VRF, maybe the LISP VRF, and you type in ping or trace route, and you will see your trace routes will flow over here, and the responses will come back. So you already have tools. We don't have to invent a LISP ping or a LISP trace route, that sort of thing. And if you decide to trace route from this source to this destination, you find the 3-segment path. The first segment path is the path through the IGP. Then you find the path between the ITR and the ETR, and then you find the path from the ETR to the destination host. All those will show up in your trace route. So we don't use tunnel mode where the ITR, ETR hop looks like one hop because people want to know which way the network is taking. So you find the path that the EIDs are taking, you find the path that the locators are taking. Do you want to add anything or not yet? I'll have to speed up to get to you. I'm going to breeze over this really quickly, but because I want to get Dave to tell you about deployment because I think it would be more of interest to this group. But we do have a mechanism for locator reachability which we keep out of the mapping database. If D1 goes down, or its link goes down, or the PE goes down, we don't take the locator out of the mapping entry and then tell everybody about the mapping entry. That will be too much, the frequency of that will be too great, and we'll then flap this mapping database. So we're doing locator reachability inside the data plane by using these locator reachability bits. And as long as these two guys are up, they're advertising both of themselves with these bit patterns saying that they're up. So these guys know to load split traffic. And when one of these 3 conditions happens, D2 knows about it, and D2 then just advertises itself as being up, and then subsequent packets just flow to D2. There are issues, and there's been discussions about failures that happen here, but I don't want to bring that up now because I know we're running out of time. But so just the high order bit here is that locator reachability is not inherent to the mapping database mechanism because we want those changes to happen only at subscription time changes or policy changes, that sort of thing, which is not very often. We assume these changes are going to be once a day. And this is why we claim that LISP may not be suitable for high-speed mobility. If you have a handset on a high-speed train and your locator is changing at high speeds, do you want to update the mapping database at that rate? And our answer right now is no, you don't want to do that. You solve that with some other solution. LISP, if mobile IP or mobile IPv6 is running, it can run on top of LISP, and that all that stuff works. Now, what we have to do is, what about a LISP site that's converted has to talk to a non-LISP site? What do we do? Well, we have 2 solutions to it. One's a NAT solution, unfortunately, and one is a proxy tunnel router solution, that which we think is probably much better. And it may provide some revenue opportunity sources for providers, interconnects, governments, third parties, whatever. So we have to get all these 4 combinations to work. Well, non-LISP to non-LISP is the combination that works today. LISP to LISP works fine because you can encapsulate, and since you don't have to change the core and the sites, that's really easy. That's everything we've explained so far. But these 2 other cases we have to be able to support. We have to support a LISP site, and we call it LISP-R, which means its EIDs are actually routable. That's what the R stands for, versus non-routable. And it depends if you have PI or PA space. What we really want to do is support this last case because we want, when you convert to LISP, day 1, we want you to be proud of it. We want you to say, I withdrew my prefix from the internet core. I'm being a good citizen. You know, you're not, we have to invent some term equivalent to green, that you're L and not green or something, I don't know. Green. Yeah, something like that. So here's an example on how it would work with NATs. Let's say the left-hand side are all old systems. Right-hand side are LISP systems. That's why they're in green. Of course, their prefixes are non-routable. And of course, these prefixes are routable or nobody be able to talk to them today. So those prefixes are in routing, okay? And I made them red because they're locators. Now what happens is, if this guy wants to talk to this guy, he knows if he's a LISP site or not by looking into the alt. If he looks into the alt and he sees a prefix for 1.2/16, he knows that that site is participating in LISP. Now let me send the map request, get the map reply, and I can encapsulate. Life is good. But if I want to, that's what he does, and he encapsulates. Now this guy down here wants to send a packet to 65333. He looks in the alt and says, that's not in there. It's not an EID. Therefore, it's probably a non-LISP site. It's this site. So what do I have to do? Well, I could go ahead and inject this packet, and it could make it all the way through here because we know 65 is in the routing table. So we know the packet will make it all the way there. But we know that the return packet won't because this 1333 is not injected into routing. Remember, this guy's a LISP site. He withdrew, and he's being L or green or whatever. So we don't want that 133 to be injected. So what he has to do is he actually has to translate that source address to address that's routable. Well, he could translate it to his RLOG because we know that's routable. So if he does that, then the packet can actually go there, and it could actually return and then gets translated. So this is kind of the local uncoordinated solution where you want to do it and you don't want to be dependent on any infrastructure boxes to help you. And it's only a one-to-one NAT. It doesn't do port translation. It's a very simple form. And we think that this might be the way that you'll have to do it for IPv4. However, for IPv6, you may want to use the PTR version. Let me explain the PTR version now, and you can make your own assessment of it. So we have the same sort of thing here, and 65 is being injected into routing for these legacy sites. And so is 66 is being injected because these are the locators for the LISP site. They're being injected, of course, because they're PA addresses. Now what we do is we introduce these things called PTRs. They're proxy tunnel routers, and they're each given locator addresses as well. Okay? But what they do is they are going to represent or help connect you, the non-LISP site, to the LISP site. So they're going to inject, and this is key phrase here, very coarse prefixes into the internet. They're going to make, their mask lengths are going to be very, very small. So they're going to try to attract traffic from non-LISP sites going to LISP sites. Okay? So for instance, when this guy wants to be able to talk to www.lisp.net over here, that he's going to get a 111 back. That's going to be in DNS. That's going to be non-routable because we want this guy to be green. And so this guy's going to inject this packet, and the packet, he doesn't have to, since he has no LISP awareness at all, he's just going to send this packet into the network. Well, it's going to be attracted to the closest PTR because he's BGP advertising the EID prefix. So what we're saying here is by injecting maybe for IPv4 10 to 20 prefixes that are very coarse that describe the entire LISP infrastructure, we're able to save tens of thousands of routes by injecting 10 more. You know, you have to pay a little bit of tax. You know, it's the Obama plan. Pay a little now to get a lot more later, that sort of thing. That's kind of what's going on here. Now, for IPv6, since we have so much address space, we think these PTRs could just inject a single route, a /16 maybe, an IPv6 /16. So for IPv6, it's really zero cost. Where for IPv4, if we want people here to use their existing addresses and turn them into PIs, then there'll be PIs all over the place. So can we get away with injecting /8s, /7s, /4s, not /0s, but that sort of thing. And we spray them across this array of PTRs that could be deployed maybe close to LISP POPs, non-LISP POPs, or as, or maybe they get deployed here. We don't know the answer to that yet. But the idea is that they attract these packets, and then these guys act as proxy ITRs, and then they know that the destination is LISP, so they encapsulate the packet. And that's basically it. And of course, the return packets will go to 65.1111. Those packets will happen natively because the destination is routable. So these boxes can only go one way. And we believe that if these have to be high-performance routers, that a high-performance router, it's easy to do encapsulation in hardware because the hardware machinery is always built just to pre-pen X number of bytes that are typically fixed. And so we can actually build a high-speed box to do this easier than if it was a decapsulator. Jose?
Who operates those PTR routers then?
Third parties, governments, interconnect providers, service providers, universities, registries. Yeah, all, some, any. Don't know.
Part of what's kind of nice about it is you could always deploy a PTR for a piece of address space that you had if you wanted your LISP customers to get better performance. There's nothing that would stop you from doing that. Like, so U of O wanted to have better performance for people who are trying to reach U of O when it converted to LISP. We could we could deploy one, and then the distance between the PTR and the site that you were trying to reach would be like one hop, right? So, whereas if it was maybe deployed at Andrew's house like it is, it might have to go across, go back, out there and back, right? So there's no reason why mod, like what Dino said, is we don't want to pollute the routing, the DFZ too much, but there's no reason why you couldn't do it.
Now, and that answer could be different depending on IPv4 and IPv6. In IPv6, you may have to push it closer to the non-LISP site because you may not have IPv6 along across diameter. But for the IPv4 case, you could use what Dave said. Dave, you're up. Dave's going to talk about implementation.
So part of this was I remember talking to Dino about this early on, and right after the Amsterdam get-together, and we were trying to decide whether or not we should do an implementation. And one of the things that we decided was that we thought it'd be a lot of fun, and we wanted to have more fun. So this was pretty much fun, and it continues to be fun. So we have a prototype implementation that Dino has done, which is, it runs on a box called, I don't know if that's in this, but okay. And so the prototype implementation supports these specs that are out there on the IETF site. It's all software switching. It does LISP for v4 and v6. It does ITR, ETR, PTR, and LISP NAT. By the way, we decided not to do NAT for LISP for 6, and I still don't think people should be doing NAT for 6, but they are. Okay, so here's the platform that we have. It runs on NX OS, which is one of the 10,000 Cisco OSs. Oh no, it's only 5,000. And it runs on this, which is sort of, the Titanium is the name of the kind of, it's just a 1RU PC with a 3.2 megahertz processor in it, it's a bunch of disk, a bunch of memory, and a bunch of gig E ports in it. You can think of it like it's like the Juniper Olive was, right? It's just a POSIX kernel development environment. And it can run on the Nexus 7K and some of the service blades, and we're looking at expanding that right now. So here's the story. We started right after the Prague IETF around March of 2007. We're building a pilot network, and people keep on calling this a pilot network, but I just want to say one thing here is that what I noticed was I worked on a lot of these kind of experimental networks like the M-Bone. I worked on the M-Bone a lot. And there was a real difference here that I haven't been able to quite communicate to people yet, probably my inability to do so. But basically, in the case of the M-Bone, you were running over DVMRP tunnels, and you were never really going to do that in reality when you got to have a full deployment of multicast. Well, I guess Fenner and Van thought you were, but you never were going to build that as your real network. In the case of LISP, the way it's being built right now is exactly the way you would build it. So it's not exactly, what I'm trying to say here is it could actually evolve into the real network without changing the architecture, which is qualitatively different than, say, like the 6-bone was, right? 6-bone was running over tunnels and all of this other kind of stuff. There's over 90 release bills. I don't know what that's a statement about, Dino. Maybe we find a lot of bugs. We find a lot of bugs. And we have phase testing, system and unit testing. We have John Zwiebel there doing that. We built a network. We'll show you the network, but it's been very instructive just to get code in the field. It's been a lot of fun, and it's been very, very interesting. And then we've enlisted a lot of people who are helping us, and we'll see that. But it's sort of an all-volunteer effort, even within Cisco. It's not even within Cisco, we're not quite there and this is all sort of pro bono work on our part. So, okay, here we go. iOS implementation underway in various forms. XR is considering an implementation. OpenLisp, it's been available for a while. Luigi and his friends, Luigi's, I guess, at DT Labs now, and then these people at the University of Louvain, I believe, have been working on this. He's a couple of, and the people at NL Labs are also trying to splice into the existing Lisp network using OpenLisp. The problem is that we've evolved the Lisp spec just a little bit faster than Luigi, who's the developer, can stay with it, so they're 1 or 2 versions behind. We're looking at Linux, either native Linux or maybe even a port of Luigi's OpenBSD. And If anybody knows about other efforts, let us know. I don't know. Somebody asked me on the RRG or somewhere yesterday if there's another vendor implementing LISP, and I don't know of any. If anybody does, let me know. So we have this pilot network. I don't like that term again, but yeah, and don't worry about it. It's been out there for a couple of years. There's really more like 30 to 33 sites. It depends on who's up when. They're all over the place. We have some in a lot in the United States. There's some in the United Kingdom, all over, Uruguay, Japan, etc. We'll see a picture of that in a second. They're all on the titanium. We're working right now. Okay, so there are two guys. Luigi and his student have titaniums, but they have open LISP boxes that they're trying to get to interoperate. And then, as I said, these guys from NL Labs in Amsterdam also are trying to get going. And again, there's this version skew on the specs, which is stopping them. But they've been doing quite a bit of work trying to get going. And I really want to see OpenLISP come onto the pilot network, or whatever we want to call it, not only because it'll give us two implementations that are interoperating, but we're going to find a lot of bugs when that happens. So we're looking forward to that. We have a couple of EID prefixes. 153.16/16 was, who is on that, you'll find out that was graciously given to us by Andrew Partan, who lifted it up from UUNet at some point. And then this /32, we bought that from Aaron. They extorted it. They extorted $500 for us, experimental prefix. So then whatever your RLOCs are, so these are the EIDs, right? So all the stuff in the LISP space is numbered out of 153.16.16 or the 32. See, I can't even say that. How do you say that? 2610 D032 or whatever. I don't even know. Okay, and so all the EID stuff. So any hosts, any loopbacks on the routers are addressed out of this space, and then the RLOCs are all the ones that whatever you have. Like at U of O, our RLOCs are numbered out of 128.223/16 because that's our prefix. So there's another little piece of this. We built this LISP alt thing that Dino described, but we decided we'd number the GRE tunnels out of 240/4. Vince and Elliot and I wrote a draft saying, why don't we just take the Class E space and give it back so that people can use it? There was all this kind of politics about it, and basically it came down to the following. If you give more IPv4, if you provide more IPv4 address space, it'll slow down the IPv6 deployment. That was the argument that was made by Elaine and those types. But we're using it anyway because it's out there. Our implementation will support it. Most implementations do. Oddly, Linux will not yet. Mac OS does. Anyway, so we're using that to number all the tunnels. And we're also using 32-bit AS numbers for the alt. And we started out in AS dot, but with the big, we couldn't decide as a community whether or not we should use AS plain or AS dot, so we're supporting both. Has anybody used either AS dot or AS plain yet? Which one? Did you say yes? Which one are you using, plain or dot? You're using plain? I don't know. I can't get behind it. I can't read it. It's like, what's your AS number? Blah 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 blah, and then you have to talk for a while. Whereas if you could just say something dot something. So it was nice to have AS dot, but community is going in a different direction. So then the EID prefixes are advertised via this alternate BGP in what we're calling the LISP VRF, but it's just another VRF. Hey, by the way, how many people know what VRF technology is? Okay, so basically the only thing you need this for, you don't really need that technology. What you need is a technology where you can have another address space. Because since the GRE tunnels are in the RLOC space, those have to be separated from the EID space, and that's the main thing. If there was another technology to do that, well, maybe. But one of the things we wanted to do here was we wanted to reuse all the technology that's out there, so we didn't have to invent this. Very little code to get the alt thing to work. It just uses standard BGP stuff, standard VRF technology, and a little bit of glue from Dino.
Example of another technology would be if your router did a virtual router implementation, was been able to be segmented that way. That would be another way of doing this.
Right, because I mean the basic issue here is that the endpoints of the GRE tunnels that the alt is built out of are not in the LISP VRF and can't be. So we use that technology just so we could reuse it. Okay, so here's the friend from LACNIC out there. I'm sorry, I forgot your name already. I want you to take a look at the picture. Here's what we built for the alt. So basically the idea here was, and this is kind of the feedback that, some feedback I'd like to get from you folks, is that, I guess there's no pointer capability here. Oh, I guess you have to do this, right? So in this case, what we were thinking was, since we want these EID prefixes to be aggregated, we'd like to see the top level, sort of a top level of this hierarchy allocation consisting of the RIRs. And here I have UI because the box that we gave to LACNIC is really Roque has it, so it's at his university. So what we did was allocate a chunk of space for each one of these guys. Obviously, we don't have that much space.
Only a clarification. I am not from LACNIC. I am from LACTLD.
Okay.
The CCTLD Association, not the IP numbers.
Gotcha. Thank you. So what we did was we allocated a chunk of space to each of these guys at the top level. And then, so they advertise only the most coarse prefix amongst themselves, right, at the very top level. And then if you're in the Aaron region, you get a chunk from Aaron, and then you allocate all of these, these guys are all just pushing around a longer prefix, but still a less coarse, and then they allocate prefixes down, so all of the end sites have /24s. These guys are pushing around /20s, if I remember, because we don't have a lot of space out of /16, but it's for that purpose. And likewise, so for example, over here we've got these folks here in the UK, and Dino. We wanted to put Dino in a distant to a distant RIR to kind of get a feeling for what it would be like to rehome. So if you had gotten your EID space from RIPE because you were in Europe at one point, and then you moved to San Jose, that would be the scenario that Dino's in, right? And he doesn't have to renumber. He just has to put a tunnel up to RIPE, so that's what he has. So that's how we built this. So for example, okay, there's one other thing here. So in the Aaron case, since we had so much, we started off in North America, what we did was we put another level of hierarchy. And what these three routers here are doing aggregation sort of on the continental level. So this is sort of a quasi-geographic idea here. So these guys are continentally aggregating. These guys are aggregating for the entire planet, and these are the sites. And all of these sites are up and running. So they can all do all of these things that Dino just talked about. Okay, then we got a couple of domain names. We went through some iterations. Obviously Lisp.net and all of that stuff was going to be taken, right? I mean, and the Lisp people, the actual Lisp programming people, they went berserk. I mean, it was really interesting. It's like nobody's heard of Lisp in 100 years, and then when we did this, they went berserk. So I tried to get Scheme too, because I like statically scoping more than dynamic scoping. I couldn't get it, so it didn't work. So anyway, we put all the EIDs in Lisp4.net. So if you look at something like www.lisp4.net, you could trace to it, or you can get on that website. That website, there's a C name that points to something called, strangely enough, scheme.lisp4.net. And the reason I did that was because for a while we have a couple of mirrors of that site, and we were just playing around with what would happen if you were round robining against a lot of different Lisp sites, and you were going through this PTR infrastructure. So we took one down. I think I took it down because one of them was broken, and it caused the thing to be broken. But now there are two other ones, so I should probably put it back. And then if you go off to www.list6.net, if you have 6. Do we have 6 here? Do we have V6 here? Yeah, then this will work. Yeah, so here's the story. North America, 20, and then, we just kind of broke it up in such a way that we thought we could get enough address to, start building some of this. Now, it turns out that in some of these regions, we just don't have enough space. We need another prefix, but, /16s aren't that easy to come by. And then in 6, 6 was a lot easier to do because it's a little bit more of a greenfield. So what I thought would be interesting is like, okay, so we have a 32. If we take so where you're seeing the X here, if we take these bits and say that's the continent, and then take the next bits and say that's the region, and then, give 48s to the site, that's what you wind up with. And that works pretty well, and then the aggregation thing is really easy to see how it works. So we have a couple of things. So we've deployed. One of the things that we've been trying to do is we're trying to make sure that we're trying to make the stuff work, right? So one of the ways of seeing if stuff work is to actually try to deploy it. So we try to deploy a ton of stuff, and we've learned that the activity of deploying this has been really instructive. I mean, and you can ask John Kemp and Jose over there who helped me. I should say that. Let me say this now. John and Jose have put in a ton of time supporting me at U of O, doing this, racking stuff up, helping me, work around U of O routing things and every other kind of stuff. So they've been very helpful. In fact, this translate.list4.net, which uses the translate functionality that Dino was talking about, Lisp NAT, I had to get Jose to put a route somewhere because that's how you do NAT and so forth. So thank you for that. But you can get on www.translate.list4.net right now, and you'll see how it works. And then we have some PTRs, proxy tunnel routers. We're also trying to play with this a little bit for various different reasons. One is because we want to, work on the technology and debug the technology. But the other one is, what does it mean to put these things in different places in the topology, which was kind of what Jose was questioning about. So right now for V4 proxy tunnel routers, there's one in Andrew Partan's basement in Maryland. He had the first one going. There's one at ISC, and there's one on Roque's box, which in Uruguay. I don't know what to call that. But you'd want to have some regionally and possibly close to high traffic sites. But we're still trying to debug all these kind of things. And we've learned some stuff, like for example, the PTR needs to have very good cache management because you know what? As soon as you turn on the background, let me put it this way. The background level of scanning that's going on the internet right now is really, really stunning. I mean, every prefix is getting scanned continuously. So if you think about what that means for the PTR is going to have a way of figuring out that it's getting scanned, manage its cache, and so forth. And so we've been working on that. On IPv6, well, you know what? Shockingly, it's hard to find IPv6 connectivity out there. Fortunately, U of O has it, ISC has it, and Roque had it. So, as I said, you could go to www.list6.net. The way you get there from right here would be probably through either ISC or U of O. Somebody could trace to it and tell me right now, trace 6 to it. And let's see, oh, yeah, okay, this is a little bit out of date. I made www.list4.net be the same as www.ptr.list4.net. So either way, but somebody could trace route to www.list4.net and tell me how we're getting there now. Whether I would guess it would either go through Andrew or ISC, but I'm not sure. I haven't looked today. Can anybody see? Okay, so I'll keep going. In the process of doing Lisp, we realized that we probably should have realized this at first, but basically, once you get this level of indirection, all of a sudden you can do all kinds of different sort of things. So, load sharing in data centers, load balancing in data centers is an application that people have actually come to us and said, hey, can we use this technology for that? The truck roll thing, well, you don't have to renumber, so that's really nice. BGP free core, we're thinking about a way of doing that too. Basically, you really don't need external routes because you have this other control path, which is the map request, map reply path. You can build different kind of topologies too with flat addressing. And in fact, I think it was Peter Lothberg who was the first one who came and said, well, if I can use IPv4 and IPv6 as EIDs, why can't I use MAC addresses? And then, the answer is, well, you can. And then the next thing that he said was, can I do spanning tree? And I said, no, I don't think so.
And then you slapped him.
Yeah. Then I said, no, I don't think it's a good idea. Yeah, so you can use MAC. You can do MAC address mobility with this too. It's just really these are all kind of like things that we really never thought of, and it's kind of encouraging because when an architecture can do things that you didn't anticipate it was going to do, like the internet does, it's usually a good sign. Oh yeah, okay, here's this thing. Okay, so, obviously we work at Cisco and we're working on this, but we've gone out of our way really to have an open policy for Lisp because Dino and I and Vince and everybody else who's working on Lisp really kind of feel like any technology that's core to the internet shouldn't be encumbered by any kind of IPR. And Dino's really been great by taking the lead with, Cisco Legal and all of that stuff to try to make this happen. And so far, I think we've done pretty well. I don't think Cisco has intention. As far as I know, let me be precise about this. As far as I know, Cisco has no intention to take IPR on Lisp, and we've gone out of our way with legal to say Cisco doesn't have an interest in taking IPR on Lisp. So, and we've encouraged people like Luigi. We funded Luigi to do Open Lisp. We're trying to fund other people to do public domain versions of things like this too. So, for all of your information, we really are trying that. We've worked in the IETF and the IRTF, and I don't know if anybody follows this, but wow, we're still trying. Let me put it that way. Okay, and so it's not Cisco only, right? We have all these people involved in this, and all of the documents, everything associated with Lisp is an internet draft in the public domain. And we really would like to so this is for you guys. Anybody wants to write code, anybody wants to splice into the Lisp network, anybody wants a Titanium, we're really interested in getting more people to work with us, get more ideas. And we need research. And fortunately for us, there is a lot of research. If you Google Scholar for Lisp and Locator ID, you'll get a couple hundred hits. It's pretty nice. So it's an open effort. So here's the drafts. The first one, Lisp 11, that's the base spec. Multicast draft, well, and Dino talked a little bit about this. We haven't gotten around to multicast yet. The draft fuller Lisp alt describes the alt system. Daryl's draft on inner working describes PTR and a translate. By the way, there's a need for an operational draft here because it turns out that you need to think about filtering carefully in the environment where you have any kind of proxy tunnel router. It's not specific to Lisp because the proxy tunnel router usually changes the source address. So you get a source address coming out of your site that doesn't look like it came from what's now the site prefix. So this is true for any proxy tunnel technology. So there's a need for an operational draft here if anybody's interested in working on that. The next one, EID block, well, I try to put a stake in the sand and say, IANA, allocate us the way you usually get the IANA to do something is you write an internet draft and command them to do so. And so I just did. They ignored it, but, extorted $500 from me. This last one, okay, so we learned some lessons about the implications of the locator ID split, and we're trying, and some of them, most of them are problems that we need to solve in the technology itself. It's not specific to Lisp. And so we felt it was really an important thing to say, hey, there's these problems with this technology that need to be solved. They're not insurmountable. But the interesting thing about this is, and this goes back to, hey, we wanted to do an implementation. This locator ID stuff, split stuff, has been around since '92 or before. I think somebody, John Day or somebody told me it was actually Salzer in '75 who had the first instance of this. If anybody knows that, I'd be interested in that. But it wasn't until we got off and implemented it that we found this stuff that's fundamental properties of the architecture. So there's something to that rough consensus. Well, I don't know about the rough consensus, but there's something to that running code stuff, And okay, and then these in the middle here, some of these are older drafts, but I'll say this draft Mathy Lisp DHT thing. These guys had some interesting ideas. They thought, hey, can you use a DHT to do the mapping? It's an interesting idea. I don't really feel like they really got there, but it's an interesting idea. And these on the bottom are just the sort of the discarded mapping system approaches that we tried. And, it's important to notice this because we tried a lot of stuff. We didn't know how to do this when we started out. And, yikes, excuse me. Lisp is modular in its mapping system, so if in the future somebody comes up with a better idea, we can try and we can go off and implement it, right? And it's also not the case, it's not the case that you might not be able to do inner working between alt and another mapping system too. So there may be a way of, it's not clear to me that you couldn't do that. So these things we've tried to keep these things extremely modular so you can do all these different things. Again, so if you can and you feel like you have the energy, sign up at lisp@ietf.org. The IESG wants more people on the list. I mean, get a proc mail filter, though. I'll send you the proc mail rule for it, though, really. And then you can get some more information if you want to go through 4 or 6 to either of those sites. I've tried to keep those fairly up to date. They're actually the same site, just get from different directions. And I'm not much of a webmaster, so you'll see what I did. It's not beautiful. Oh yeah, and then here's the LISP thing. So, how do we do on time?
Perfect.
So, can we take a few questions or a few comments or anything like that? If anybody has one. Paul?
Mike. Paul, can you use Mike?
The Mike.
The Mike.
I got kind of two questions. How fast do you think those internal mappings turn over? I mean, what's the propagation problems and so forth?
Yeah. Okay. So there's two questions in that actually. So the location of the mapping, the ETR that's holding the authoritative mapping, can change as fast as BGP can change it. In other words, I could withdraw one and announce another one, and it's just BGP. So we don't really want to do that because I guess this wasn't really said. I think Dino alluded to this, but if what we do is we take all the problems that are in the DFC BGP right now and put them in the mapping system, we haven't solved anything, right? So we're really trying to avoid that churn and deaggregation in the alt mapping system. That's the first thing. The second thing is if the mapping changes while I'm holding a cached mapping for you, say, suppose you change your mapping and I'm holding a cached mapping. Is that your question?
I'm just curious about the general.
Well, so far we've seen low frequency, right? And we anticipate it will be low frequency because mappings are intended to be a subscription time kind of thing, and that has to do with, like Dino mentioned, the mobility issue. So we're thinking it's going to be relatively static because you don't rehome your site on much more quickly than like on a daily basis, right?
Yeah, I mean, it seems like I'm a DNS guy, so I think this in DNS terms, but it seems to me that, a half-hour TTL there with some way to detect failure when you go to an egress path that all of a sudden is dead.
Yeah. Dino's got, what is our TTL right now?
24 hours.
So 24 hours, but we're just learning that right now. But we have the mechanisms that you just described.
But you're talking about a reachability issue, and you'll go to an egress box that will see the list of locators regardless if they're up or down. It will have separate status bits knowing if it's up or down by hearing data packets from it and using those locator reachability bits. So I made it maybe not clear enough, that we do not take locators out of the mapping database when they go down. So they're always there. They always describe what your connectivity to the internet is, but it doesn't mean if you're up or down. It just means I know that I have these CPE boxes connected to these two providers, and those are the locators to use. And when I'm about to use them, then I look at these other set of bits called reach bits to find out if they're up or down. And that was the locator reachability slide where we were showing. Okay.
And how often do those bits change, do you think?
Those bits can change pretty quickly depending on if routers go up and down or the site partitions and stuff. Those are being transmitted in the data plane, so we do have some good fast convergence there. But for only a certain class of failures, if you and I are CPE routers and we have our links each out to the net, and my IGP can detect that you've went down or of our sites partitioned, and when that happens, when we both now are encapsulating packets to remote sites, the locator reachability bits, before I said I'm up and Paul's up, and now I'm saying I'm up, and you're saying you're just up. So people that want to be able to get one way or the other will use the locators that they hear from. Okay.
What's kind of nice about that is the remote site can detect partition in the distant site.
Yeah, and it's done in the data plane, so you don't have control plane propagation time. You don't have the traditional queuing delays that you have in the control plane. You still have the queuing delays in the data plane, just regular packet queue delays and that sort of stuff. But you're transmitting this reachability status in the data plane.
One other thing is, you want to talk about SMR a little bit?
Yeah, go ahead.
Go ahead. You can That's if you want to take one out or add one, right?
Right. So I mean, are you okay on that? On the way we now, what we want to go on to mention next is what if you do change service providers and now that locator no longer is relevant and you want to either replace it with a new locator or just remove it from the locator set? What do you do there? And I talked briefly to you about it at the last NANOG, but I'll mention it. We have this thing called an SMR bit. It stands for solicit map request. And as I'm sending data packets to you, and somebody configures a locator to be removed from the locator set, I can, at my site, I can then say that I can rate limit who I send SMR bits to, so I can control the rate of map requests that come to me. So by me setting this SMR bit to you, I'm telling you, the remote site, to send me a map request. And when you send me a map request, I'll give you a map reply with the new information.
Yeah, there's new information. It's basically you're signaling new information for you to come back and get from
So
you.
we're using the same query reply, but this SMR bit is a notification of change, rather than, if you know the trade-offs, right? If I had to push this new mapping to everybody, I'd have to remember who is requested from me, and we know that's not going to scale very well.
Yeah, I think you're implying much more understanding than I really have. But my other question is, when you add these extra wrappers, I mean, what are the sort of MTU and packet size issues that you get into?
Okay, great question. So there is a, we answer that question 3 ways. The first way is, and it's the easiest way to answer it, is that we want to say, and we know it's not totally true everywhere in the universe, that most, maybe 80% of the links and routers today support 4470. So we have plenty of room not to exceed MTU when 1500 byte packets are sent from the host. That's the easy answer. Everybody's going to raise their hand. Not true, because I go through a DMZ that is 100 meg Ethernet, and I have 1500, and your LISP is slapping headers on it that it's making it go to 1540 or 1600 or whatever. So what do you do? So we have 2 approaches. We have a stateless approach and a stateful approach. The stateless approach is that when the ITR wants to encapsulate and realize it's going to go over the 1500 limit when it puts the header on, it will then fragment packets and then encapsulate each one of them. It encapsulates them, sends them to the ETR. The ETR decapsulates and forwards each fragment, putting the onus of reassembly on the host. That's one. The stateless one is we run MTU discovery. And the way we do that is the host sends the ITR a packet. The ITR just encapsulates it. It sends the packet if it can. If there's any path along the way that violates the MTU, we get an ICMP2 big message back. The ICMP2 big message comes from an intermediate core router back to the ITR. The ITR then notes what the effective MTU is, stores that 16-bit value in the mapping entry, and then sends the 2 big message all the way back to the host. The host lowers it, so when the next packet comes, we can put enough on it to be within the effective MTU. So that later approach is the stateful approach. Comments, questions, opinions, tomatoes? Oh.
Ann.
So, slightly different question. Back in Dino's slide set, you had 4 connectivity cases. One was non-LISP to non-LISP, the next one was LISP to LISP, and then there are 2 cases where you have LISP to non-LISP. Now, can you say anything yet about the performance implications? In other words, the current state of the world is non-LISP to non-LISP pretty much. How do any of those other 3 cases compare? Not so much, well, obviously there's 2 parts. There's the getting started part, which you've gone through in substantial detail, but there's also, once you've actually got the connectivity up, the steady state place. So if you have any thoughts, or you've been able to do any instrumentation, or you have hints about what people should expect, it also, of course, points out what's the story going to be. Is it going to be possible to claim that, in a wonderful marketing world, the LISP world will be lower latency or faster or better in some performance sense than the current non-LISP world?
Yeah, I'll just take an operational view of that. Basically, with respect to non-LISP to LISP case, the non-LISP to LISP case, there were 2 solutions to that, right? One was this LISP NAT thing, and that has virtually, as far as we can measure right now, the impact of that is negligible, right? Because that's just NAT, right? I mean, that has the same properties NAT has, right? Exactly, in fact. Now, when you're talking about this proxy tunnel router thing, it will have, the performance, the question you asked is multidimensional in the space of that, and I'll just give you a couple of them. One is, if you're the first one to ever use the proxy tunnel router for the destination, then it's exactly equivalent to being behind a LISP world and asking for that destination. So whatever the mapping delay and latency is with that, okay? But there's another issue there, another dimension, and that is how far away from you, you're the source, is the proxy tunnel router, and then how far away is the destination, right? So we played around with that a little bit, but that is actually something that I think might be able to be monetized. Because if I'm AT&T or whoever, I'm a giant, and I decide I'm a LISP world now, and what I want is for people trying to reach my customers who are in the LISP world from outside, I have an incentive to put up a proxy tunnel router very close to the edge of my network, because I'll be attracting the traffic in the sort of on the path that it would go on, right? Not this whatever, So the first one we put up was at Andrew's house, right? And it had this horrible property that, if I wanted to send a packet to myself at U of O, I had to send it across the country and back, right? And so we recognize that right away, and that's just a property of any of these proxy tunnel techniques, for any protocol that does it, right? But then we started kind of messing around with that and saying, well, what could we do to optimize that? And so then we put one up on the ISC DMZ, and that just changed the performance properties of a lot of things, So your question is really good, but the space is multidimensional.
So I was going to throw out the easy ones first. You talked about the complex cases. Thanks for doing that. So the LISP to LISP case and what latency is going to be added. So basically an encapsulation, decapsulation step are the extra things that are happening when a packet flows from a source to a destination across these multiple domains. And we've seen from many hardware implementations over the decades that encapsulation is not costing you that much. It's pretty much in the noise. So I think as long you still will have your shortest paths between the two sites. So we won't see long latencies because of path changes, and you'll still get shortest path between there. And so the question is the encapsulation, decapsulation, does that hurt you? And it's pretty non-existent. So I think that case can run as well as the case for non-LISP to non-LISP as you see it today. Arguably, you might even get better paths because it's the shortest path to the last hop AS versus going through some circuitous policy path. So we might get some better paths. Not sure. That's good. We'll have to do a lot of trace routes to figure that sort of thing out. Dave said most of the ugly stuff that I wanted to avoid about the PTRs. If the PTRs are not placed close to where the sources are, they will have to go far, of course. And to what I thought Paul's initial question is how long does it take to get mappings? What I just did as an experiment on Friday was, since Dave said I'm connected to RIPE on the alt thing. So I have a 2 megabit upstream link through Comcast, and that's where I was sending my map request through over the GRE tunnels to RIPE, which was somewhere in the UK, in Links, or where is it in?
The RIPE router, it's in Amsterdam.
It's in Amsterdam, okay. In Amsterdam. And the RTT by the time I get the map reply back, it was about 100 milliseconds, which was kind of surprising. So that's what it would take. If you had a fire hose of data, you'd be dropping 100 milliseconds worth of data for the first packet that went from this site to that destination site. And then everything else is everybody benefits from the cache.
Yeah, there's an interesting, important point there that I think frequently gets overlooked, is that latency, the first packet latency, is only for the first packet between the sites. Every other packet and every other host that sends a packet to the remote site now gets to use that mapping entry. So it's only the first packet between sites.
In reality, what is it? It's probably a DNS packet that gets dropped or a TCP SYN that's going to be transmitted 3 seconds later on the first connection that starts up from that. So I don't know if it's that much of a problem. We see this all the time on large layer 2 networks when I want to open up a TCP connection to you over a layer 2 network, and ARP's going to do the same thing, right? So.
And, in sort of less quantitative studies that we do sometimes, because, you have this, it's 30 node network. It's not tiny. It's tiny. It's not insignificant in terms of its geographical distribution, is what I'm trying to say. Is that once the thing is up and running for a while, you really can't tell it's there from the user perspective. I know that's a qualitative thing, but you really can't, and we've done a little bit of trying to quantify that, but we need to enlist some researchers, who have time for some of the measurement folks, the CADAs or whatever, to really put some discipline around that. Are we done? Others? Okay, well, thank you guys. And I was instructed to tell you, I didn't want to say this too early, but apparently the food's back over on the other side. So, all right, thanks everyone.
Thanks a lot.